Hi everyone, welcome back. Today we're going to talk about a different type of equilibrium, and that's going to have to do with solubility and what happens when an ionic compound dissolves. So what we're going to be talking about is something called the solubility product constant. This is another type of equilibrium constant, so capital K, but now the subscript is SP for solubility product. And we have to think back to what we already know about ionic compounds. So remember that they're strong electrolytes and that when they dissolve in water, that they're going to dissociate completely into their positive and negative ions. But the question is, how much does the compound actually dissolve? Because none of that dissociation can happen unless the substance dissolves. All right, so what we're asking ourselves here is, how soluble is the compound? So let's take a look at barium sulfate as an example. So this is a fairly insoluble compound. And what actually happens when it dissociates is just like other chemical reactions, it's going to set up an equilibrium. So any barium sulfate that gets dissolved in the water is going to dissociate into positively charged barium ions and negatively charged sulfate ions, in one of each. All right, and so we can write an equilibrium expression for this process, just like we can any chemical reaction. Remember that we only include substances that are aqueous or gas, and in this case, they're all going to be aqueous, and that anything that is a solid or a liquid, we leave out of our equilibrium expression. So this barium sulfate on the left is going to be left out entirely. So our KSP expression, our equilibrium expression here, is going to look like this. KSP equals concentration of barium ions times the concentration of sulfate ions. So remember, it's always product over reactants, and if there's no reactants that are aqueous or gas, we just leave those out entirely. So I want you to pause and take a second and make sure that you can write the KSP expressions for the dissociation of calcium fluoride and silver sulfate. All right, so here are the solubility constant expressions for each of these compounds. So calcium fluoride, remember, is CaF2. When it dissociates in solution, it's going to form one calcium ion with a 2+ charge and two fluoride ions with a -1 charge. So our KSP expression is going to include only those aqueous ions. So KSP equals concentration of calcium ions times the concentration of fluoride ions squared, because of the 2 in our equation over here, because of that coefficient. For silver sulfate here, silver sulfate is Ag2SO4. It's going to dissociate into 2 silver ions and 1 sulfate ion. So our KSP expression is going to be the concentration of silver ions squared, again because of that coefficient of 2, times the concentration of sulfate ions. All right, so a little bit more about solubility and the solubility product constant, this K right here. This equilibrium constant K is a measure of how much solid dissolves to form a saturated solution of our compound. And just like all equilibrium constants, it has no units. So it functions just like any of the other equilibrium constants that we've talked about already, KEQ, KC, KP. It has no units. Typically, if KSP is less than 10 to the -10th, we'd say that our substance is very insoluble. So the bigger the number, the more soluble. But when we use that word solubility, we are talking about something that does have units. So when we talk about the solubility of a substance, the units that we're going to use for that are either grams of solute per liter or moles of solute per liter, and you'll recognize that this one as molarity. We're going to talk about how the solubility of a substance can change depending on conditions like the pH of the solution and the presence of common ions in the solution. But the important thing to remember is that, like other equilibrium constants, KSP is only going to have one value at any specific temperature. So that KSP can change when the temperature changes, but it will not change. Because of any of the conditions of the solution. All right, so now we're going to talk about how to work a couple of different types of practice problems that have to do with KSP, and we're going to talk about how to get the equilibrium constant from the solubility and how to get the solubility from the equilibrium constant. And for both of these, we want to use our ICE tables, just like we've been using for our other equilibrium problems. So we're going to work one together, and then I'm going to have you work one on your own. So for this first question, we're looking at a saturated solution of silver chromate at equilibrium. And we can see that it has a silver ion concentration of 1.3 times 10 to the negative fourth molar. So we're going to set up an ice table together to calculate KSP for this compound. All right, so here I have summarized the information that I was given in the problem. So I know I've got silver chromate, I know my equilibrium concentration of silver ion, and I'm looking for KSP. All right, so where I want to start is I want to write what's happening. So I've got silver chromate solid, which is dissolving and setting up an equilibrium to form 2 silver ions and 1 chromate ion. Okay, anytime you've got an equilibrium problem, it's a good bet that you want to write up your equation first so you know what reaction am I talking about, what's actually happening. Now I'm going to set up my ice table here. So remember, initial concentration, change in concentration, and equilibrium concentration. The good news is anything that is not a aqueous substance or a gas is not going to be included in any of our calculations. So I'm just going to draw a line through for all of these for the solid because that's not really going to be involved in any of the calculations. It's not going to be in our KSP expression. So we know that when we first put our solid into the water, that initially we're going to have none of our product. We're not going to have any ions. And then as the substance starts to dissolve, we're going to add 2x silver ions for every 1x chromate ions because we get 2 silvers and 1 chromate every time 1 silver chromate dissolves. All right, and now thinking about what else we know that our equilibrium concentration of silver is 1.3 times 10 to the negative fourth. All right, so we're given that information, and we also know that if we started with no chromate and we added X amount, that our final concentration is going to be X. All right, so what we want to do is be able to plug in everything that we need for our equilibrium expression. So let's write that. So we've got KSP equals silver ion concentration squared times chromate ion concentration. We know silver's concentration, but we need to figure out chromates so that we can plug in and solve for KSP. All right, so if 1.3 times 10 to the negative fourth equals 2x, we can divide 1.3 times 10 to the negative fourth by 2, and that's going to tell us our value for x. So x in this case is going to be half of 1.3 times 10 to the negative fourth again, so that's going to be 6.5 times 10 to the negative fifth. So now all I have to do is plug into my equilibrium expression here, 1.3 times 10 to the negative fourth, and then don't forget to square that number, and then times 6.5 times 10 to the negative fifth. The answer when we plug this in for our KSP is going to be 1.1 times 10 to the negative 12th. And again, we're not going to use any units on our equilibrium constant. All right, so now that you've seen how we work this problem, I want you to try the second example here. So we've got a saturated solution of magnesium hydroxide, and we know that at equilibrium, the hydroxide concentration is 1.48 times 10 to the negative fourth molar. So pause the video and see if you can figure out KSP for this compound. All right, so check your answer with mine here. Again, we should have our equation for what's going on, magnesium hydroxide dissolving to form magnesium and 2 hydroxides. Our initial concentration, we leave out everything with the magnesium hydroxide. The other 2 have an initial concentration of 0. We're adding plus X magnesium plus 2X hydroxides. And we know from the problem that our final concentration of hydroxide is 1.48 times 10 to the negative fourth. So we know that that is equal to 2X. We can again divide by 2 to figure out that X, or our magnesium ion concentration, is 7.4 times 10 to the negative fifth molar. Then we can plug into our KSP expression, which will be magnesium concentration times hydroxide concentration squared, plug in what we got from our ice table, and we'll get a KSP of 1.6 times 10 to the negative 12. All right, so now we're going to talk about how to go the other way, how to calculate the solubility if we're given the KSP. And again, we're still going to use an ice table here. All right, so the first one, the KSP for calcium fluoride is 3.9 times 10 to the negative 11th at 25 degrees Celsius. And assuming that calcium fluoride dissociates completely, I want us to calculate the solubility of calcium fluoride in grams per liter, and that unit's going to be really important there. All right, so again, I've sort of summarized the information given in the problem here and what we're looking for. And we'll start off with our calcium fluoride and show that when it dissolves, it dissociates into calcium ions and 2 fluoride ions. Okay, so for our ICE table here, again, nothing for the calcium fluoride because it's a solid. Starting with no calcium and no fluoride, adding X, adding 2X of the fluoride. And now we don't know those final concentrations, so our equilibrium concentrations there are going to be X and 2X. Now we need our KSP expression. So we're going to have calcium fluoride squared. And now we know our KSP, so we can plug in our KSP and we can solve for X here. So it's going to be 3.9 times 10 to the negative 11th equals X times 2X squared. Remember that if we square 2X like this, that equals 4X squared times another X here, so that's going to equal 4X cubed. So 3.9 times 10 to the negative 11th equals 4X cubed, and we'll solve for X here. When we solve for X, we get 2.14 times 10 to the negative 4th. And remember, we had concentrations here in our KSP expression, so the unit for that is going to be moles per liter times 10 to the negative 4th moles per liter. Now our question asks for solubility in grams per liter, so we just need to do a little bit of stoichiometry to get this into grams per liter. So we're going to multiply times the molar mass of calcium fluoride here, which is 78 grams per mole. And when we do that, moles are going to cancel, and we're going to get that the solubility of this is about 1.7 times 10 to the negative 2 grams per liter. So that means 0.017 grams of calcium fluoride will dissolve in 1 liter of water. All right, so now try one on your own. So given that the KSP for LaF3 is 2 times 10 to the negative 19, I want you to calculate the solubility in moles per liter this time. All right, so here you can check your answer. So this time we're splitting into 1 lanthanum ion and 3 fluorides. So we've got X and 3X for our final concentrations. In our KSP expression, we have to remember that our fluoride ion concentration is going to be cubed. So we plug in X and 3X cubed equals our KSP given in the problem. So we get all of that. That KSP equals 27x to the 4th. And when we solve for X, we get 9 times 10 to the negative 6. So only 1 sig fig here. And then because these are concentrations, this is already in units of moles per liter.